Picture a 5-year-old spending 20 solid minutes wiring up a circuit to light an LED, then bolting outside to check if her cardboard solar collector's gotten warm yet. She's not just playing around, she's engineering. My name is Chloe Miller, and I've spent years watching kids this age grasp genuinely complex technical concepts when we give them the right tools. You're listening to the STEM Lab podcast. Quick heads up. The research, the data, everything you're hearing has been thoroughly vetted and written by real educators and specialists, but the voice delivering it is AI generated. Just wanted to be transparent about that from the start. Now, to everyone who's been listening for a while, seriously, thank you. Your time matters, and I don't take it for granted that you choose to spend it here. If you're brand new to the show, welcome aboard. You're about to hear straightforward, no-nonsense guidance on STEM toys and learning tools that actually build real skills. New episodes drop every Monday, Wednesday, and Friday, so subscribe if you don't want to miss them. Let's jump into today's topic. The best STEM toys for 5-year-olds don't just keep kids busy. They lay concrete technical foundations for sequential skill building that continues straight through elementary school and well beyond. At this age, developmentally appropriate engineering tools should build spatial reasoning, introduce cause and effect system thinking, and establish hands-on iteration habits. These are the skills that prepare kids for screen-free coding transitions and eventually text-based programming down the line. Here's my quick verdict. Prioritize open-ended construction systems with real engineering constraints, screen-free logic toys that mirror computational thinking, and renewable energy kits that teach physical principles while building ecological awareness. Now, let's talk about what to actually look for in STEM toys for 5-year-olds. First up, developmentally appropriate skill milestones. Forget those vague age labels. 5-year-olds are developing fine motor precision and sequential thinking. They can follow 3 to 5-step processes independently and understand that actions produce predictable outcomes. The toys you choose should target these capabilities explicitly. Think snap-together circuits that require hand-eye coordination, block-based programming mats where moving pieces in sequence creates results, and construction kits with mechanical cause and effect relationships, like gears that turn wheels or weights that trigger motion. These constraints build problem-solving resilience and spatial reasoning. Contrast this with toys that light up and make sounds regardless of how parts connect. Those teach kids that errors don't matter. Look for systems with mechanical honesty. If a gear train is supposed to demonstrate speed versus torque trade-offs, the gears should actually mesh, not just sit near each other while a hidden motor does the work. If a solar panel kit claims to teach energy conversion, the panel should noticeably perform differently in shade versus sunlight. I once tested a solar robot that ran on hidden button cells with a decorative solar panel glued on top. That's not education, it's greenwashing. Reject products that fake technical function. The best tools at this age also support open-ended building. Proprietary systems with one-use-only pieces limit long-term value. Standardized connectors like Lego-compatible pieces, magnetic tiles with consistent polarities, or modular electronics with uniform snap interfaces let you expand the system as skills grow. Now let's talk about screen-free foundations that prepare for computational thinking. 5-year-olds don't need screens to learn programming logic. In fact, screen-free coding approaches build deeper foundational understanding. Look for tactile sequencing toys, mats where kids arrange arrow tiles to program a path, or robot mice that execute commands entered via buttons on their backs. These teach algorithmic thinking, breaking tasks into ordered steps, debugging by identifying which step went wrong, and iteration, trying variations to improve outcomes. These are core computational skills they'll apply later when transitioning to Scratch and Python. The practical specs matter here. Battery requirements, whether it's rechargeable via USB versus disposable AAA cells. Durability for repeated use. Can the toy survive drops and sticky hands? And expandability. Can you buy expansion packs or integrate with other systems? A $40 screen-free coding toy that breaks after 2 months is worse than a $60 option that lasts 3 years and connects to future kits. Sustainability design and life cycle considerations. This is non-negotiable for me. STEM toys for 5-year-olds should be built to last through multiple children and ideally should use recyclable materials or renewable energy principles in their design. Avoid battery-dependent toys where batteries cannot be recharged. You'll burn through dozens of disposable cells over the product's lifetime. Instead, prioritize solar-powered options, USB rechargeable systems, or entirely mechanical designs requiring no power. Check for consumable dependencies. Does the toy require proprietary refills, subscription access, or single-use components? Those ongoing costs add up, and they teach kids that technology is disposable. Better to invest in robust, open systems that accept standard parts. I've repaired and modified solar kits in my workshop for years using off-the-shelf components. That's the kind of long-term thinking I want to model. Also, consider material toxicity and manufacturing ethics. BPA-free plastics, FSC-certified wood components, and brands transparent about supply chains earn trust. Your 5-year-old will mouth parts, and you'll touch these materials daily. Choose thoughtfully. All right, let's get into our top picks. First, the Thames and Cosmos Kids First Science Laboratory. Check the link below to see the current price. This kit introduces fundamental physical science through 26 hands-on experiments spanning chemistry, physics, and biology, each designed specifically for 5-year-old attention spans and safety requirements. You'll notice immediately that the equipment is scaled for small hands, oversized beakers with sturdy bases, large print instruction cards with clear sequential photos, and no glass components. The kit builds observation skills and hypothesis testing. Kids predict what will happen when they mix baking soda with vinegar, then observe the actual result and compare. This cycle mirrors real scientific method without requiring abstract reasoning they don't yet have. It requires no batteries or electricity, includes reusable lab equipment like funnels, measuring tools, and goggles, plus consumables like citric acid, baking soda, and food coloring. Expect consumables to last 8 to 12 months with weekly use. Replacement chemicals are available separately, or you can substitute standard household ingredients. The durable plastic components withstand drops, and instruction cards are coated and wipe clean. Here's what works well. It builds scientific process foundations, predict, observe, conclude, without screens. Reusable lab equipment transitions into future chemistry kits as skills advance. Open-ended experimentation is encouraged. The manual includes variations for extending activities, and the parent guide explains why each experiment matters for skill development, not just how to do it. The downsides: consumables create ongoing cost, though you can substitute grocery store alternatives for most. Some experiments produce minor messes, so you'll need a dedicated workspace or easy clean surface, and instructions occasionally assume adult co-facilitation, not fully independent for all 5-year-olds. Next, the Gravitrax Starter Set. Check the link below to see the current price. This is a modular marble-run system that teaches potential and kinetic energy, momentum transfer, and cause and effect engineering through hands-on construction. Unlike traditional marble runs where marbles simply roll downhill, Gravitrax incorporates magnetic cannons, hammers, and spinners that redirect motion in surprising ways. Kids quickly learn that track height and curve radius affect marble speed, and that certain configurations fail. Marbles don't have enough momentum to climb an upward section, for instance. This iterative trial and error builds persistence and systematic problem solving. The system's expandability is its greatest strength. Dozens of expansion packs add new physics elements like bridges, trampoline plates, and transfer modules, and all pieces are cross-compatible. You're not buying a single toy. You're investing in a years-long learning platform that scales with capability. I've seen Gravitrax setups in high school physics classrooms, demonstrating centripetal force and energy conservation. The same principles your 5-year-old explores intuitively. No batteries required for the starter set, though some expansions include motorized elements requiring 3 AAA batteries. Minimum build space is about 3 by 4 feet for starter configurations. Serious builds can expand to table size. Plastic components are highly durable. Magnetic elements maintain strength through years of use. What works? It teaches physics principles through direct manipulation rather than abstract explanation. Truly open-ended building. No single correct solution fosters creative problem solving. It expands across age ranges, remains challenging and relevant through elementary and middle school, and pieces are standardized and compatible with all Gravitrax expansions, preventing obsolescence. The cons. Starter set alone offers limited configuration options, so plan to budget for expansions. It requires significant flat surface area for complex builds, and small marbles present a choking hazard for younger siblings, so storage discipline matters. Moving on to the Ingeno Discovering STEM Simple Machines Kit. Check the link below to see the current price. This kit builds working models of levers, pulleys, gears, wedges, screws, and inclined planes, these 6 fundamental machines underlying all mechanical engineering. Each model demonstrates a concrete principle. The pulley system shows how distributing weight across multiple ropes reduces lifting force. The gear assembly illustrates speed versus torque trade-offs, and the lever models reveal fulcrum placement's impact on mechanical advantage. These aren't decorative builds, they're functional tools your child operates to see physics in action. What sets Ingeno apart from competing construction kits is its explicit skill scaffolding. The instruction manual doesn't just show assembly steps, it explains why engineers use each machine type and poses experiment questions. What happens if you add another pulley? Does the load get easier or harder to lift? This guided inquiry approach prepares kids for systematic STEM investigation methods they'll apply in later project work. Requires no batteries, includes approximately 60 building pieces like beams, connectors, gears, axles, and pulleys. Plastic components are thick and reinforced at stress points. I've tested them under loads well beyond normal use, without failure. Compatible with other Ingeno sets for expanded building options. This strengths directly teaches mechanical engineering fundamentals used in actual industry applications. Models are genuinely functional. Kids see immediate real-world cause and effect. Educational content is exceptional. The parent guide includes extension activities and career connections, and durable design supports years of repeated assembly and disassembly cycles. The drawbacks. Some smaller connector pieces require fine motor precision that frustrates younger 5-year-olds initially. Limited free building flexibility compared to more open-ended construction systems, and the instruction booklet's text-heavy explanations may need adult translation for pre-readers. Next up, the Solar Rover Science Kit. Check the link below to see the current price. This assembles into a functional solar-powered vehicle that moves when exposed to direct sunlight. No batteries, no hidden power source, just photovoltaic energy conversion in action. 5-year-olds grasp the connection immediately. Cover the panel, the rover stops. Tilt toward the sun, it speeds up. This hands-on demonstration of renewable energy principles builds intuitive understanding that classroom lessons can't match. I've built similar solar vehicles in my own workshop, and the engineering fundamentals here are honest. This is how real solar-powered systems work, just scaled for small hands. Assembly requires adult help for initial build, approximately 30 to 45 minutes, but once constructed, operation is fully independent. Kids experiment with panel angle, shade patterns, and surface types. Carpet slows the rover, smooth floors let it zoom. This self-directed exploration teaches hypothesis formation. I think it'll go faster if I add more light, then testing and observing results. The kit includes a basic explanation of photovoltaic cells appropriate for kindergarten comprehension. 0 batteries required, operates solely on solar power, requires direct sunlight or bright halogen lamp. Standard LED bulbs don't provide sufficient intensity. Plastic construction is moderately durable. The gear train can jam if exposed to sand or debris, so indoor or clean outdoor use is recommended. Pros. Teaches renewable energy through direct experience rather than abstract concepts. 0 ongoing costs. No consumables or subscriptions. Encourages environmental awareness and ecological literacy from early age. And it scales into progressive learning paths. Kids can modify the design as skills advance. Cons. Requires specific lighting conditions to function. Indoor lighting is often insufficient. Initial assembly complexity demands adult co-building, and single configuration design, limited expansion or modification options without advanced skills. Now, The Code and Go Robot Mouse Activity Set. Check the link below to see the current price. This introduces sequential programming logic without screens through a tactile coding interface. Kids program the robot mouse's path by pressing directional buttons on its back in sequence, then watch it execute those commands across a gridded maze mat. This hands-on approach builds algorithmic thinking, breaking a goal like "get the mouse to the cheese" into discrete, ordered steps. When the mouse doesn't reach the target, kids debug. Which step was wrong? What sequence correction is needed? These are exactly the computational thinking skills that transfer to Scratch and Python years later. The included maze pieces reconfigure into dozens of layouts, and the clear grid structure helps kids visualize distance and directionality. You'll see them develop spatial planning skills as they mentally trace routes before programming. The kit also supports collaborative problem solving. Two kids can work together, designing mazes and testing each other's solutions. Requires 3 AAA batteries, not included. Robot mouse measures approximately 4 inches long. Durable ABS plastic housing withstands drops from table height. Maze board tiles are thick cardboard with protective coating. Expect 2 to 3 years of regular use before significant wear. Battery life is approximately 15 to 20 hours of active use. What works? Teaches programming fundamentals like sequence, loops, and debugging without screen time. Tactile button interface builds fine motor skills alongside computational thinking. Reconfigurable maze pieces provide high replay value and progressive difficulty, and it directly prepares kids for block-based coding platforms they'll encounter later. The cons. Maze pieces are cardboard rather than plastic, can curl with humidity or rough handling. Programming is limited to directional commands, no variables or conditional logic yet, and it requires flat surface approximately 3 by 3 feet for full maze configurations. Finally, the Magformers Basic Set. Check the link below to see the current price. This uses magnetic construction tiles to build 2D and 3D geometric structures, teaching spatial reasoning, geometric properties, and structural engineering through intuitive play. Each tile contains embedded magnets that automatically orient to attract, never repel, so pieces snap together regardless of how kids position them. This forgiving interface lets 5-year-olds focus on design rather than struggling with mechanical connections. You'll watch them discover fundamental architecture principles. Triangles create rigid structures, squares flex and collapse, and 3-dimensional forms require specific tile arrangements. What makes Magformers exceptional for this age is how it scales. Initial builds are simple, flat shapes, basic pyramids, but the system supports years of advancing complexity. Older kids build geodesic domes, intricate vehicles with moving parts, and towering structures demonstrating cantilever principles. The magnetic system is also highly durable. I've yet to see magnets fail, even after years of heavy use. Consider this a decade-long investment rather than a single-age toy. No batteries or power required, BPA-free plastic with sealed neodymium magnets. Each tile measures approximately 3 by 3 inches. Set of 30 pieces fits in standard shoebox-sized storage container, compatible with all Magformers expansion sets and accessories. The strengths. Builds spatial reasoning and geometric intuition through hands-on manipulation. Forgiving magnetic interface prevents frustration. Kids focus on design, not fighting connections. Exceptional durability and decade-plus lifespan. Serves multiple children. And truly open-ended building with progressive complexity spanning ages 3 to 12 and beyond. The drawbacks. 30-piece starter set limits build size and complexity. Plan for expansion purchases. Higher per-piece cost than traditional building blocks, and magnets occasionally detach with extreme force, like throwing or stepping on them. Generally repairable with superglue. Let's tackle some frequently asked questions. What skills should STEM toys for 5-year-olds actually build? 5-year-olds should develop spatial reasoning, sequential thinking, fine motor precision, and systematic problem solving through their STEM toys. These are the cognitive foundations that support all later technical learning. Spatial reasoning means understanding how objects relate in three-dimensional space, which piece fits where, how rotations change orientations. Sequential thinking involves breaking multi-step processes into ordered actions. Fine motor precision enables manipulation of small components, and systematic problem solving teaches kids to test hypotheses, observe outcomes, and iterate improvements, core computational skills they'll apply later. Look for toys that explicitly target these capabilities rather than vague creativity or fun claims. The best tools present real engineering constraints that teach cause and effect relationships, circuits that don't light up unless connections are correct, structures that collapse if weight distribution is poor, or programs that fail unless commands are properly sequenced. These experiences build persistence and analytical thinking. Avoid toys that function the same regardless of how kids interact with them. Those teach that precision doesn't matter. At this developmental stage, you're establishing habits of careful observation, systematic testing, and learning from failure that will serve them through university engineering programs and professional technical work. The specific domain matters less than the quality of thinking skills the toy cultivates. A well-designed marble run teaches problem-solving just as effectively as a coding robot if it requires genuine iteration and presents honest physical constraints. Do 5-year-olds need screen-based coding toys, or should I stick with unplugged options? 5-year-olds learn computational thinking more deeply through screen-free, tactile coding toys because physical manipulation builds stronger neural pathways than abstract screen interactions at this developmental stage. Screen-free coding robots with button interfaces or directional tiles teach identical algorithmic concepts, sequencing, loops, debugging, but with sensory feedback that anchors learning. When kids press buttons on a robot's back to program movement, they're building procedural memory through physical action. When they arrange arrow tiles on a mat to create a path, they're manipulating tangible representations of abstract commands. This embodied learning translates more effectively to later text-based programming than early screen exposure. Research from MIT's Developmental Technologies Group confirms that concrete manipulative experiences in early childhood support stronger abstract reasoning later. Screen-based coding tools add unnecessary abstraction. 5-year-olds don't need to learn tablet navigation alongside programming concepts. Save screen-based platforms like Scratch for ages 7 to 8, when abstract thinking capacities mature and kids can manage the cognitive load of both interface manipulation and code logic simultaneously. The transition from screen-free to block-based coding works smoothly precisely because foundational algorithmic thinking is already established through physical practice. That said, if your child already has significant positive screen time experience and shows readiness for digital interfaces, block-based coding apps designed specifically for 5-year-olds can work. Prioritize options with large, clear controls and immediate visual feedback. But if you're choosing between screen-free and screen-based options for a child new to coding concepts, the tactile choice builds stronger foundations every time. How do I know if a STEM toy will actually prepare my child for advanced learning versus just being a fun distraction? Effective STEM preparation tools teach transferable technical skills with career progression pathways, not isolated tricks or entertainment features. Examine whether the toy's learning objectives connect with industry standard practices and later educational stages. Ask yourself, does this toy teach a specific, named engineering principle, like mechanical advantage, electrical conductivity, or algorithmic sequencing that I can identify? Can the skills practiced here transfer to more advanced tools later? Does the manufacturer specify what capabilities kids should gain and how those connect to subsequent learning? For example, a marble run teaching momentum and energy transfer prepares kids for formal physics. A circuit kit teaching series versus parallel connections introduces electrical engineering fundamentals. A screen-free coding robot teaching sequence and iteration builds programming foundations. Contrast these with toys that light up and make sounds but involve no problem solving, present no genuine constraints, or work identically regardless of how kids interact with them. Those are entertainment, not education. The presence of failure states is often diagnostic. If the toy can fail, circuit doesn't complete, structure collapses, program doesn't reach goal, and kids must debug systematically to succeed, it's teaching real technical thinking. If everything triggers rewards regardless of input quality, it's not. Also check whether the product fits into a progressive learning path. Can you see what comes before this skill level and what comes after? Quality manufacturers design product lines spanning multiple years with clear skill progression. Single-age toys with no expansion pathway often lacked educational depth. Finally, look at the instruction materials. Do they explain why concepts matter and where kids will encounter them again, or just show assembly steps? The toys I recommend for 5-year-olds explicitly teach principles they'll apply in 7th grade science, high school robotics competitions, and eventually professional engineering work. That's the continuity that defines real preparation rather than temporary engagement. Should I prioritize STEM toys that run on batteries or look for renewable energy alternatives at this age? Prioritize renewable energy and battery-free options for 5-year-olds whenever technical quality is equivalent. This builds ecological literacy alongside engineering skills and avoids teaching disposable tech patterns you'll spend years correcting. Solar-powered kits, USB rechargeable robots, and entirely mechanical construction toys eliminate battery waste while demonstrating that technology doesn't inherently require disposable consumables. My solar rover kit from childhood still works decades later because it has no battery compartment to corrode. Many battery-powered toys from that era died from leakage long ago. The ecological principles matter too. 5-year-olds who learn early that sunlight can power machines develop intuition about renewable energy systems that serves them throughout their education. When they build solar vehicles and wind turbines at this age, they're establishing mental models of sustainable technology as the norm, not the alternative. That said, some exceptional STEM toys unavoidably require batteries, coding robots with programmable memory, for instance, and I won't reject an educationally superior product just because it uses AAA cells, but make the conscious choice. If you're comparing two similar quality circuit kits and one runs on solar while the other needs batteries, the solar option teaches an additional valuable lesson at no educational cost. When you do choose battery-powered toys, strongly prefer USB rechargeable designs over disposable cells. They're more sustainable, more economical over the product lifespan, and they teach kids that energy is something you steward rather than consume and discard. I've seen parents spend hundreds of dollars on disposable batteries over the years for toys that could have been solar or rechargeable from the start. That's money better invested in additional educational equipment. What's the realistic durability and lifespan I should expect for STEM toys for 5-year-olds? Quality STEM construction toys should last 5 to 10 years of regular use serving multiple children, while electronic components typically provide 3 to 5 years before battery compartments corrode or motors fail. Budget and plan accordingly. Building sets with durable plastic components like Lego, Magformers, or Ingeno essentially last indefinitely if stored properly. I still use Lego pieces from the 1980s in current projects without issues. Magnetic tiles embedded magnets can occasionally detach with extreme force, but generally maintain strength for a decade. Wooden construction toys offer similar longevity if they're solid hardwood rather than particle board. Electronics introduce failure points. Battery contacts corrode, motors accumulate dust in their gears, and circuit boards can crack with rough handling. Expect battery-powered coding robots to provide 3 to 5 years of active use before maintenance needs arise. Solar-powered options avoid corrosion, but have motors that eventually wear. That said, many robotics toys are repairable if you're comfortable with basic soldering and mechanical cleaning. I've extended the life of several broken robots by simply cleaning motor contacts and replacing battery springs. For consumable-based kits like chemistry sets or crystal growing experiments, the reusable equipment, beakers, goggles, measuring tools, should last many years while the actual experimental materials obviously deplete with use. Consider this when evaluating cost. A $70 construction set your child uses for 8 years costs $9 per year. A $35 electronic toy that breaks after 2 years costs $17.50 annually. The higher initial investment often delivers better long-term value. To maximize lifespan, establish storage discipline early. Parts organizers with labeled compartments prevent loss and damage, and teaching kids to return toys to designated spaces builds habits that protect your investment. Design your home STEM lab infrastructure around durability from the start. Dedicated workspaces, proper storage solutions, and clear handling expectations extend equipment life significantly. Also consider expandability. Toys that accept new components or integrate with other systems justify higher initial costs because they grow with your child's capabilities rather than becoming obsolete at the next developmental stage. Here's the bottom line. The STEM toys for 5-year-olds you choose now become the technical foundation your child builds on for the next decade. Choose tools that teach real engineering principles, present honest physical constraints, and connect to progressive skill pathways rather than isolated entertainment. Prioritize open-ended construction systems that expand across age ranges, screen-free coding tools that build algorithmic thinking without digital abstraction, and renewable energy kits that teach both physics and ecological responsibility. You're not buying toys, you're equipping a home STEM lab with foundational instruments that prepare kids for industry-standard tools they'll encounter in high school robotics programs and university engineering coursework. Invest in durability, expandability, and manufacturers who transparently connect their products to concrete learning outcomes. Your 5-year-old's circuitry experiments today become their Arduino projects at 10 and their summer engineering internship prototypes at 17. That's the continuity that transforms play into genuine technical capability. That wraps up this episode of the STEM Lab podcast. Thanks for listening all the way through. As always, new episodes come out every Monday, Wednesday, and Friday, so you've got a steady stream of STEM education insights coming your way. If you found this helpful, leaving a 5-star rating and a quick review really does make a difference. It's how other parents, teachers, and caregivers actually discover the show when they're searching for reliable guidance. And go ahead and hit subscribe or follow so the next episode shows up automatically the moment it's live. Talk to you soon.